So we carry on with our explanation for chapter 3, railway traction systems, and we have reached section 9. We will be talking about AC power supply. There is a DC power supply and there is AC power supply for railway applications, and AC power supply can be common in high-speed trains, and DC power supply can be common in metros. So for example, London Underground have a 625 kV, while the main line in the UK have 25 kV at 50 hertz. So without further ado, let's have a look at AC power supply. The topics that we'll be discussing in this section are feed arrangements and systems in common use. We'll mention some of the systems in Germany, some of the systems in mainland Europe, and also we'll be talking about AC power supply arrangements, and we'll be talking about as well as AC substations parameters and components, catenary arrangements, ground current effect, booster transformers, and auto transformers, power factor, and harmonics. So feed arrangements and systems in common use, AC power supply issues, some of the issues that is facing AC supply, AC substations, what are they consist of and what are their main parameters, catenary arrangements, how these infrastructure components that are holding the lines is being arranged, and ground current effect, what happens to the return current and what is the possibility of that current to infiltrate the ground, and what are the consequences of that. Booster transformers and auto transformer, and booster transformer is the transformer that is responsible for handling ground current. This looks like an auto transformer. Also, I'm not 100% sure, but this looks like an auto transformer. Power factors and harmonics. Where are the losses and how we can avoid those losses? So section number 9.1, feed arrangements. Long railways are fed from a number of substations spaced along the line. So these substations are spaced along the line. An example of a system is the UK. Is in the UK, where you have three-phase power are available for different voltages. Maybe you get this through your substations, 400 kV, 275 kV, 132 kV. You need to understand what are the supply companies transmit power at what voltage. So, for example, let's assume they supply voltage at 33 kV, 22 kV, 11 kV, and other voltages down to 415. So the railway company has to organize with the electricity company to make sure that they have the voltage that they need, and then they transfer that voltages to what is they utilize in their railway lines, and this happens on the substation. So for example, the substation will transfer, for example, 33 kV if you are in Germany, and this is the company that you choose, to 15 kV at 16.7 hertz. This is in Germany, Austria, Norway, Sweden, and Switzerland. That's an example of what is the AC system that is being used. In the UK, it's 25 kV, and in some countries, it's 50 kV. So are the systems that are in common use, and you get this from the electricity company. It can have a supplying range between 33 to 11 kV. It depends on different companies. Now, AC power supply. The AC power supply, reliability of the supply. What are the issues that are facing AC power supply? There is reliability of supply, making sure that this company will always have a reliable service, and you can depend, and your train service can depend on that level of reliability. In-feed duplication, so you get that duplication in your feed, and duplication of transformers. These are issues. You have transformers that are supplied from the electricity company, also from the railway company, and they result in duplication. So you need to be careful with that. Phase imbalance, you have different loads, and this can cause a problem. Leakage current, and we'll talk about this in more details, the ground current effect. Power factor and harmonics, having losses in the network, so you need to try to reduce these losses. Line resistance, the resistance of the overhead line, and flicker load variability, you have that flicker. So these are some of the issues that can face your AC power supply system. Now, let's talk about substations, and we talked that the AC power supply usually is supplied to the network through substations, and they have 5 to 10 kilometers between each other. So if you have a 100 kilometers line, you might have 2 to 3, maybe 4 substations, and they supply between 10 to 15 megawatt capacity. And they should supply overload capability. They should be able to supply 150% extra for 1 hour, 300% for 1 minute, and 45% for 10 seconds. So they also should consider overload. A network may need complex arrangements of substations, but you just remember we have a substation every 10 to 50 kilometers, and it supply the railway line, and it gets its feed from the national grid. AC substation components, what does these substations consist of? They have transformers, switch gears, protection relays, and SCADA. These are some of the examples of the substation components. Now let's talk about the catenary arrangements, how the lines are being held up in the air. There is a simple catenary like this one, stitch catenary like this one, and this is associated with rigidity and structural engineering more than it's associated with electrical engineering, or compound catenary. And the ground current effect, so let's read this. Return currents traveling unrestrained can travel at a depth of down to a few hundred meters to the ground. This would have, depending on soil conditions, this would have a major effect on, for example, telephone lines. Telephone lines would be impacted with your return current filling the ground. Also, it can introduce dangerous voltages to any line side conductor, any wire or machine that is on the ground. It can energize that. So there are various methods that are deployed to avoid this ground current effects. One of them is booster transformer, and the second one is auto transformer. So booster transformer and auto transformers. So booster transformers are different than auto transformer, and let us have a look at the picture. So this is your supply transformers coming from the substations, reaching your overhead line. Now the current is moving, providing the train with the current, but now you have a return current. And in your return current, you want to get rid of that so it does not fill the ground. You've put a booster transformer and another booster transformer in your return current. It uses 1-to-1 ratio transformers to draw the return current into a special return conductor. So now the whole return current has been dissipated, and transformers are fixed to catenary support structure every few kilometers. So you have this booster transformer every few kilometers. In the case of auto transformer, why it looks very much similar, you have your supply current coming, then it feeds the train, and now it goes to the auto transformer. The problem now with the auto transformer is they control the return current and reduce the supply current to 50%. They reduce what is coming to 50% by using a supply voltage double that required by the train. So they use the supply voltage double what is used with the train. This is a kind of the mechanism that is used, and the auto transformer is a center tab on a single coil transformer. So this is a single coil, and this is what is the auto transformer. And they are becoming increasingly popular worldwide. So you need to know that you would put your auto transformers or booster transformers every few kilometers, and you need to see how they can control your return current. Now, power factors, we talked about there are some issues of losses because of power factors, and you would try to control this by using pulse width modulation front-end converters. With AC drives, largely avoid creating a problem. I think what is important that you remember that power factors can happen, and you need to use all the tools necessary to try to reduce the power factors. A power factor of 1 means there is no losses. The lower the power factor is, the more the losses within your network. This was the end of chapter 3, the end of railway traction systems. We talked a lot about if we start from the beginning, we talked about AC power supply, DC power supply. We talked about traction packages, We talked about motors, AC motors and DC motors. We talked about braking system. So the full cycle of getting train in an electrified railways has been discussed. Also, we talked about autonomous traction, diesel, hydrogen, and definitely we talked about some of the basic concepts of physics to calculate the tractive efforts and electrical circuits. And we talked about also power electronics. So this gives you a very nice and comprehensive overview of railway traction and how it's happened. So now you know what's an induction motor, you know what's a DC machine, you know what's an AC what's an AC power supply, what's a DC power supply, you know what are the voltages that are being used in metros around the world, you know what's an autotransformer, you know what's a booster transformer, you know what's a rectifier, what's an inverter, you know. And now you are very much familiar with the traction packages. You know what's an air brake, you know what's an electromagnetic brake. So now you have got this understanding of how railway traction systems work and how they help in moving the trains forward or braking them, propel and retard the main functions. So it's up to you to try to take this knowledge to a greater depth and focus on a specific topic. Or you can just carry on and understand the other railway systems. There are many railway systems. That was only the traction system. We discussed the traction system, the rolling stock system, and we talked about railway planning and operations. There are still more. So stay tuned, and we'll see you in the next chapter. We'll be talking about systems engineering. Have a great evening and see you in the next chapter.